Okay, good morning, everyone. So we have our first midterm coming next week, right? So get ready for it, and it will cover everything which we have studied, including today, up to today. So these slides are included, chapter 4. Okay, and sample was released. I hope you have gone through it and you got the idea. So if you have any questions, you can reach me. Okay, so any questions about previous lecture? No? Looks like I'm a very nice, very good teacher. You understand everything. Every day I ask any question, and most of the time there is no question. I hope you show good performance then on the exam. Okay, so we were talking about last week about how we can implement the threading sport uh, in the system. And to answer that, we found we have two options. Either we can implement the threading sport as sport for implementing the multiple threads at the level of at the user level or user space or at the kernel space. So we basically talked about only first option, which was like what are the pros and cons if we implement the threading sport at the user space. So can anybody quickly tell me one advantage of implementing the threading sport at the user level? What is one plus side of implementing the threads at user level code?
You have more precise control over when the threads are open and closed.
Not necessarily, because you can do the same thing also in the kernel level. Yeah, go ahead.
Compatibility, even if the
Say louder.
compatibility, even if the kernel doesn't support.
Yeah, that's not called compatibility. What you are saying is correct, but the terminology is not right. That is called portability. So even when your kernel is not aware of any idea of the threads, kernel doesn't support threads, but if you are implementing at the user level, so you can still use the threads in your program because they are a user level concept. Like let's say if I am using a library to implement threads, and that library is available, I download and install that library on Linux, on operating system 1 and on operating system 2. So assume operating system 1 is aware of the threads, operating system 2 is not. But it doesn't matter for me because I am implementing threads at the level of the user code. So it doesn't matter for me. So I can run the threads on both operating systems. And what is one downside of implementing threads at the user level?
If there's a hold, the whole program stops.
If there is what?
If there's a, I think it's called a hold, or whenever
Okay.
there's a system called
I got you what you mean, yeah.
In that case, that since the kernel thinks that program is just a single thread, the whole thing stops.
Yeah. So your friend is right. So when the threads are not supported at the kernel level, what does kernel do is that it treats all the processes as a single threaded process. So it doesn't matter whether you at user level you are using multiple threads or not. So even if you are using multiple threads at the user level, your process has multiple threads at the user level, but kernel views it as a single threaded process because it is not aware of any idea of threads. So now what happens, let's say you have 10 threads in your process or your program, and one of those threads makes, let's say, a blocking system call, for example, read. So if the read is not successful, all other threads, the remaining 9 threads, they will also be blocked, which means they will not be able to make progress or will not be able to continue their execution, which is against the basic idea of multi-threading. What is the basic motivation of multi-threading is that if one thread is blocked, we don't want other threads to block. We want them to continue, even if one of them is blocked. So this is like, it kills the basic motivation, okay? So that's why we move to the second option, which is that we support the threads at the level of the kernel, not at the level of the user space or user level code. So here the difference is, if you remember the figure from the previous lecture, here the difference is that yes, we have multiple processes in the user space, and each one of them has multiple threads. But in the kernel level, what we do is that in addition to the process table, which we always have, in process table you have one entry for each process. In addition to that, you have thread table. The difference is that if you are implementing the threads at the level of the user level, then this thread table exists in the user level space. Here it is existing in the kernel level space, and now one entry for each thread. So now kernel is aware of the metadata which you need to successfully run the kernel, successfully run the threads. So for example, the program count, it is aware of the program counter of each thread, or the stack pointer of each thread. So all the thread specific information is visible to the kernel and is maintained by the kernel. Okay. So kernel is aware of the threads, and if a user process Okay. So if a user process invokes a system call, oh, sorry. So here the difference is that if we want to create or destroy a thread, so we have to make the system call. This is different from the user level implementation, where to create or destroy a thread or to schedule a thread, the APIs which you invoke, they are user level functions, which basically mean that you pay the less cost. Whenever you make system call, you are paying more latency, because you are trapping into the operating system, and then once the system call is completed, you go back to the user level code. Okay, so if you compare it with the user level implementation, this is kind of a disadvantage. Okay. Also, I have already said this, that kernel maintains a single thread table for all the threads in the system. This is important to note, that thread table is not specific to a process. It is for all the threads in the system. And while in the user level implementation, each process had its own thread table, okay, because it is a process local thing. And this table is updated on creation or destruction of the threads, and each entry holds only thread specific information. And here, the important point here is that now if one thread is blocked, like let's say you have a process, again, giving the same example, you have one process with 10 threads, and one of them makes a blocking system call, and that call is not successful, so the thread is blocked. It doesn't mean that all other 9 threads of the same process are also blocked, because those threads are implemented by the operating, so the operating system views them as separate entity, not view the whole process as a single entity. So what does the kernel do? It will select an other ready thread from the same or a different process to run. This is different in the case from user level implementation. Let's say in a user level implementation, one of the threads is not blocked by by a blocking system call, but actually it is not ready to run. Maybe it is waiting for some operation, but it is not the blocking operation. So what will happen? So in user level implementation, what will happen, that your scheduler will select another ready thread from the same process. But here in the kernel level implementation, because kernel can view that all the threads of running in the system, so it can select a ready thread from the same process or from a different process. Okay. Okay, so now if we look at the trade-offs or pros and cons of this approach. So one thing is that positive point is that if a single system call, if a blocking system call happens, or let's say if there is a page fault, we will talk about page faults later on when we will be talking about virtual memory. But for the time being, you can assume that page fault are more or less similar in their behavior to system calls. Okay. So if there is a blocking system call or page fault by one thread, it does not block all other threads of the same process. Also, a thread cannot occupy the CPU forever. Remember when we were talking about the user level implementation? So a thread had to release the CPU voluntarily, which means it had to call the thread yield API or the function. If let's say you are writing the code and you are writing the code for your thread in user level and you forgot to include the thread yield, and your thread got the chance to run, then after that it will never release the CPU. Assuming, let's say, if there is an infinite loop, and there is no thread yield. So as a result, what will happen that other user level threads will not be able to get a chance to run on the CPU. But this is not the case here because kernel is aware of the existence of the threads. So what does kernel can do? It can like maintain or it can allocate the time budget just like processes to each thread. And if a thread is like taking too long to complete, kernel can simply kick it out and schedule another ready thread. But the problem in this approach is that, as we said, we need to use the system calls for creation and destruction, so they are expensive. However, to mitigate the cost of thread creation, what we can do is we can do something which is named as thread recycling. So the idea here is that when you destroy a thread, you actually don't destroy the thread-related metadata. More specifically, a more right way to say is the thread-specific data structures. But you only mark that thread as not runnable, which basically means that now you are not going to schedule this thread for the execution on the CPU, but you keep its data structures. So data structures are basically, for example, remember we talked about thread table. So in thread table, you have one entry for each thread. Now, if one thread is destroyed, so there you have this entry still there, but what you do is that you reuse that entry for a new upcoming thread which you are going to create in the future. Okay, so you keep its kernel level data structure, reuse them for that. So actually you avoid the cost of recreating the new data structure for the new thread. Okay. However, there are also some other issues when we are using multiple threads. So remember we talked about the fork system call, which is basically that if you want to create a new process, so process A can invoke the fork to create a new child process, which will be exact duplicate of the parent process, right? So let's say that the parent process is a multi-threaded process. And then one of those threads, let's say parent process A has 10 threads, and one of those threads invoke the fork. So now a new process is created. Now the question is that this child process, which is created as a result of fork, should it have multiple threads, like same 10 threads as the parent process, or should it have only a single thread? So we will maybe not touch on this issue in this set of slides, but maybe you can go and read the book related section. But here is the issue that depending upon your requirement, you can specify the policy. Like for example, if you the child process is, let's say, if you want it to be single threaded, you can specify that, okay, don't create all the 10 threads, just duplicate one thread which is invoking the fork. So duplicate it. The child will be the single threaded process. But if it is a situation where you want the multi-threads to be duplicated, all the threads to be duplicated, you can also specify that. So actually you provide both options and you leave it up to the programmer or the user to use which one of those two options. Okay, any questions? Okay, now we have talked about how we can implement the support for multi-threading. What are the two different options? What are their trade-offs? But it is like it is possible that you have user level threads and the kernel level threads at in the same system. So how we map the user, so how we actually map the user level threads to the kernel level threads, which basically mean that here, okay, let me pose this question. Let's say if I create a user level thread and my kernel is also aware of thread existence. So, and in a single process, let's say again, I have 10 threads. So these 10 threads, are they handled by a 10 user level threads in the user process? Are they handled by a single kernel level threads? Are they handled by 10 kernel level threads? Or they are handled by 5 kernel level threads? So basically it means that uh, if you have only, let's say if you have only one kernel level thread which is responsible for handling all these 10 user level threads, it's mean kernel is treating your 10 threaded process as a single threaded process because it is implementing only one kernel thread to take care of these 10 user level threads, which basically means what? Which means that at a time, only one user level thread will get the chance to run on the CPU, even when your kernel is aware of the, it has the idea or concept of the threads, but since you are saying that I will create only one kernel thread to take care of 10 user level threads, so the scheduling is done by the kernel, right? So what will happen that the whole process will still be treated as a single threaded process from the kernel's perspective. So which basically mean that these multiple user level threads will not be able to run at the same time on multiple cores. Even let's say you have 8 cores, but since you have only one kernel thread, you will be using only one CPU at a time. So which basically means that if we want to increase the concurrency, then we should be able to make multiple kernel level threads responsible for handling the multiple user level threads. Okay. So one option, so this is known as mapping, like how many user level threads are mapped to how many kernel level threads. So the one option is, which I just gave an example. The first option is that you have one to many. So which basically means that many user level threads, they are mapped to single kernel thread. So in the figure, you can see you have like multiple user level threads and only one kernel level thread is responsible for handling them. So from the kernel's perspective, this like process with 4 threads is treated as a single threaded process. So it has the same issue. If one of those threads make a blocking system call, so all other threads are also blocked. And as I said, even if you have multiple cores available on your platform, you will not be able to run all the 4 threads at the same time because the scheduling is done at the level of the kernel threads, and only one kernel thread is responsible for handling all of them. And like most of the systems, they are not currently using this approach. It is obvious why they are not using this approach, the lack of concurrency, right? The other option is that we do the one-to-one mapping. So each user level thread is mapped to each independent kernel level thread. So whenever, like for example, if you are whenever in your user program, whenever you invoke a API to create a user level thread, it will automatically also create a corresponding, the OS will automatically create a corresponding kernel level thread to take care of your user level thread. So you will have more concurrency compared to many-to-one mapping. I think the title of the previous slide was not correct. I said one-to-many, where actually it should be many-to-one, not one-to-many. So here you have more concurrency than many-to-one because now you can schedule them or you can run them on multiple cores at the same time, assuming you have multiple cores available. But the issue is that number of threads per process, they are sometimes restricted due to the overhead. Why we have overhead? Because you are creating one kernel thread for each user space thread, right? So creation means not only the time latency, but it also means doing managing more metadata. So, and definitely to manage metadata, you first have to create the data structures. So it becomes more expensive as you create more and more threads in terms of latency and in terms of the metadata. But this is the most popular approach, which is currently used in many operating systems like Windows and Linux. So the problem with the last one, the first approach was like many to one was that we have lowest concurrency. Here you have highest concurrency, but then here you have the problem of overhead. So maybe that what we can do is that to address this problem, we can strike a balance where we like have multiple user space threads still, and we have multiple kernel space threads, but we don't do one-to-one mapping. What we can do is that we have many-to-many mapping. Which basically mean that you allow many user level threads to be mapped to many kernel threads. Maybe like you can say two of these threads are taken care by one kernel thread, and then these two of them, both of them have their own corresponding kernel space thread. So in this way, you try to achieve the better concurrency as compared to the case of many to one, but you try to pay the lower overhead as compared to the case of one to one. So it allows the operating system to create a sufficient number of kernel threads, sufficient in the sense which are enough for the purpose of your application, depending upon your specific use case. How many threads are sufficient for you to get the enough performance. But it is difficult to implement because basically then you need to track that, okay, which user level threads are mapped to which particular kernel thread, because there is no one-to-one mapping anymore. Examples, Windows with the thread fiber package. So like this is the case where this approach is used, but otherwise this is not very common. Most common case is one-to-one. Why it is not common? Because now the more modern multi-core platforms have sufficient number of cores to let the user achieve their required level of concurrency. So it's not a big issue. Maybe, for example, even in your project, if you see, I have asked you to run it with like up to 256 threads, right? So if you have completed your project, you may have seen, and even in the sample output, you may have seen that your output, your performance starts saturating maybe at 64, right? So maybe if 64 threads are enough. So like 64 cores are enough for you at a time. That is a big number, but I mean, compared to the old times, it was considered difficult to be achieved. Yes.
So for this many, would you basically just like set a maximum number of kernel threads and then they just allocate it based off of that? Or is it like some sort of context that reasons why certain kernel threads map to multiple user threads and certain one-to-one threads?
Okay, before I answer that question, first we need to understand this, like, yes, you can create as many kernel threads as you want, but creating the threads more than the number of cores, physical cores you have is not going to pay you any advantage. Right. Okay, so it's mean that if you get the best performance you will get is up to the number of threads same as number of cores, right? And let's say you have 64 cores, so you create 64 kernel threads at the same time, and then you have multiple user threads, like let's say 128. So then what you can do is that you can say, okay, each kernel thread will be responsible for 2 user threads. So yes, there is a practical maximum limit in the sense that if you go beyond that, you will see the diminishing improvement in the performance. You will see some performance improvement, but as you will keep going, it will be like become negligible. Yeah, I hope I answered your question. Did I? Okay. Okay, so we have talked about at what level to implement the threads, and also we have talked about how user level threads are mapped into the kernel level threads. And now we are going to talk about some thread libraries. Specifically, we will talk only about one of them, which is pthread. So, but what is the thread library? It provides an API for creating and managing threads. So by now you should be aware of like what is API, because it is just a specification. It is not implementation. So like I give you only the interface of a function. Like for example, I say do the sum of, let's say I multiply A and B. Okay. So the interface is I give you input A and B, and output I expect is like, let's say C. C is equal to A times B. Now the internal implementation is up to you, how you do it. Maybe you multiply it, or maybe you do the repeated sum. Up to you. I don't care. Okay. So API is the same thing. So this is just an API. So library provides you just an API for creating and managing the threads. So there are like, again, we have, we can implement the libraries both as we have talked about earlier, either at the user level or at the kernel level. And they have the same pros and cons. I think you don't want me to go over them because these are the same things which we have talked about earlier. So examples of the thread libraries are POSIX, like Portable Operating System Interface, which is named as POSIX pthreads library, Windows threads, and Java threads. We are not going to cover the last two. We are going to talk about only the first one, which is pthreads. Okay. Yeah. So POSIX standards, it is a standard for defining API for thread creation and management. As I said, it is only a specification, not an implementation. Implementation, you can implement the internal implementation can be different. And this standard is implemented by Unix, Linux, and Mac OS. You can implement it as both user level library or a kernel level library. Then question to me, the initial question to me was like, okay, does Linux implement pthread as user level library or kernel level library? The short answer is that it is implemented as kernel level library in Linux. And the long answer is you can visit and read this link. Okay. So it will give you the details about what does it mean that when you implement the library at the kernel level. Okay. So before we see specific examples of thread creation and management using the pthread library, let's first talk about two related concepts, which are synchronous and asynchronous threading. So the synchronous threading is where parent thread, it must wait for its children thread to terminate before it resumes. Basically, I don't know whether it is the right word to say or not, the parent thread terminology, but basically what I'm trying to say is that the creating thread must wait for those threads which are created by it to be completed before it resumes its execution. And asynchronous threading is that where parent thread doesn't wait for the children thread to complete and terminate before it can continue. So which basically means that all the threads run simultaneously and independently. So here is our example. Suppose that we want a parent thread to create multiple children thread, and then we want those children thread, like we have 4 children thread, and then we want all of them to do separate tasks. I'm keeping it very simple because I want you to focus not on the logic of implementing the example, but basically I want you to focus on how to create and destroy the threads, okay, and how to allocate them the tasks. So the first child, it is responsible for, let's say, printing all the numbers in the range from all the even numbers in range 1 to n, child 2 odd numbers 1 to n, child 3 prints the squares of the numbers, and child 4 prints the cubes. Okay. Okay, so this is the sample code for the single-threaded program, which I think is very trivial. I mean, all of you know how to write the single-threaded programs, so it should not be an issue here. So I'm not going over it. Just let's say I'm just doing some initial things, getting the timestamp, then I'm calling the function print even number, odd number, print square, print cubes, and then get the end time and take the difference and print how long it takes for all this to complete, right? And this is your just header file, which define all those functions, print even, odd, scales, and cubes, and this is your make file. So everything looks familiar, right? Okay, so this is the multi-threaded version of the same thing. So here what we are doing is that first thing is that I'm including a different header file. I will show it later on, but I mean different header file as compared to the single-threaded version. Second, let me walk you through this block of code, this part of the code. So first we are creating an array of pthread underscore t, which is basically a data type which you can use to store the thread ID. So TID is the name of the array, and it has 4 elements because we are going to create 4 threads. And when we create them, when you create a thread, you will be given back the ID of that thread, and we will store it. We will store it here. Okay, so okay, maybe we can stop here. I will cover this after the break. Okay, so let's have 10-minute break and then we can. Okay, let's get back to the lecture. So we were talking about this multi-threaded version of, yeah, go ahead.
So I just had a quick question. For the kernel level thread table, how is that implemented in memory? Is that like a contiguous part of memory? So like a hash table?
To be honest, I'm not sure about that, but it can be implemented in multiple ways. A table you can implement. You can have contiguous memory and you can also have linked lists. But the idea is that you basically should be able to index the each entry.
Yeah.
So I'm not sure how it is implemented in Linux. You need to check it. But
I'm just wondering about the overhead that would be.
but every implementation will have its own pros and cons. For example, if you are doing a linked list and you don't have direct pointers to each entry, then you need to traverse all the entries. But if you are implementing it as an index table based on some key, so then you can, like, if you have the key, you can directly reach to the that particular entry. So the search time will be lower. Okay, so so here we were talking about this these 4 lines of the code. So first you need to store the IDs of the threads somewhere. So when you're using the pthread library, you can use the data type of pthread underscore t to store the IDs. Here we have like we are making an array with the 4 entries because we want to create four threads. Then I am creating here a function pointer array, which basically, again, it also has 4 entries. Why? Because I want each of those threads to execute separate functions. So what I'm doing here is that I'm creating an array of type void static. I'm giving it name function pointer with 4 entries, and I'm initializing it with the name of those 4 functions which I want to invoke, which I want threads to invoke these functions. Okay, and then I am also defining a variable attribute of type thread attribute, which basically you can use. This type allows you to specify the attributes of the threads. So basically, if you go and look at the documentation, so this data type has like different fields. It is a structure which has different fields, and each field specifies different attributes. So here what I'm saying is that, okay, initialize this attribute variable. Basically what I mean is that initialize the attribute structure with default values. For example, what will be the priority of the threads, right? Then I'm simply getting the timestamp, and then I'm invoking, then I'm running a for loop to create 4 threads. For that, I'm calling this API pthread create. And what is the interface? That you have to first specify the variable where you want to store the ID of the thread, which will be created by this API pthread create. So I'm specifying, okay, store the the ID of the created thread in this entry of the TID array. And then for all the threads, I am saying that, okay, start the thread with the specified attributes, which is basically the default attributes. But later on, you can, if you want, you can also change the value of different fields in this attribute data structure by using, I think, pthread set attribute. Okay, so you can go and check. Then I'll specify what function need to be executed. So create a thread, store its ID in this variable, create the thread with these default attributes, and then assign this created thread, this function to be executed. So I'm just providing the function pointer and then the entry in the index of that function pointer. This one, okay. And then I'm specifying the argument for the function pointer, for the function which I want this thread to execute. So if your function, it doesn't have any parameter, you can specify null. But if it has some parameters, so you need to specify the argument for that function. So for example, here I'm saying and n. So what is n here? N is like I'm getting it from the user. So which is basically if I want to print the number from 1 to n, so that is this. Okay. And if you want to, like, let's say if you want to pass multiple parameters, so there is only here you can specify only one argument. But if you want to pass multiple parameters to the function, what can you do? You have taken programming language courses, right? So what can you do? Define a structure, initialize it with all the parameters, and then provide here the address of that structure. Okay. But still, you will be passing only one argument, but inside it will have multiple parameters. Okay. And here, then in the same main function, what I'm doing after creating the threads, I'm again running a for loop where I'm in the body, I'm saying, okay, pthread join. Basically, the pthread join basically means that wait for all those children threads which I have created for them to complete and join the parent. After completion, after their completion, they join back the parent. So then I'm specifying, okay, wait for which of those threads. So I'm specifying the ID which I have already stored in the array. Okay. And if you want the thread on which you are waiting, it will also return you its exit status. But if you don't want, you can simply specify the null. But if, let's say, if you want to get the status of that thread, exit status of that thread, you can specify here a variable, address of the pointer variable. So the exit status will be copied into that variable. But here we are not, we don't read it. And then we are just doing timestamping and getting how much total time it takes to complete the multi-threaded task. This is the, how to say, these are the functions which I have, which we have in the multi-threaded number example .h header file. The only difference is in this header file as compared to previous one is that here, not only difference, but one main difference is that we are including the pthread.h because this is where you have all the library implementation, API, implementation of all the APIs. So you need to include it, which basically mean it will give you it will allow you to call pthread create, pthread join, or pthread exit. Okay. So, and also other functions. So here, what we are doing here is the body of the function is same as in the single threaded case. The only thing is that here, once we are done with whatever functionality we want to do, after that we are saying pthread exit 0. So basically, once you exit, the parent thread which was waiting for it will receive the notification that okay, this signal is this thread has completed now, and then your parent can proceed. Once all the 4 threads, it has received the information that all the 4 threads have completed. Okay. And I think, okay. And there is also some little difference in the make file. So maybe you just need to look at this one, the how to compile the multi-threaded version. So the only difference here is that we need to specify the pthread library. So as basically stands for library. So this is the syntax for GCC. So, and then after the L, you specify the name of the library which you want to include. So here we want to include pthread library. So we are just saying include the pthread, L pthread. Okay. So, and that's all. Today's lecture was relatively short because I have to go for a talk. So, you have a question? Go ahead.
Shared memory, like what we do for the project, or does that, what are we gonna come with that?
He is asking that does the pthread, the multiple threads created in the pthread library, do they use the shared library just like in project one or not? Anyone who want to answer this question? You can do my job, right? Anyone who want to answer this question? So the threads, all these threads which I created, they share those that data which is global. They share the text segment. Actually, we talked about in the start of this set of slides. Not this setup, but like when we start time. So they share the data segment, they share the text segment, they share the heap segment, which basically mean that if you go to this example here, okay, so so here, if you look at this in header file, do I have any global data? Let me check. If I have any global data, then it can be accessed. I don't have any global data here, but if you have any global data, then it is visible to all the threads. Let's say if you have created an array of numbers 1 to n with elements n elements in the header file, instead of like saying, okay, I'm giving you, instead of specifying n as a number, you specify an array and initialize it, then all the threads will be able to see it. Okay. Yeah. Any other question? No? Okay, then that's all. And good luck with the exam.